Okay, I'll wait just one more minute. Right, can you see my, Santosh, can you see my screen and voice is all right?
Yes, sir.
You can start. Okay, good morning again. I'm happy to see that most of you have stuck through with me. And so today is the last of this block of lectures with quite an eclectic introduction. I've just looked at astrophysics, particularly naked eye astrophysics, with in various ways, just to give the basis of what is to come in the rest of the course, because a lot of this is going to be useful for understanding the later courses. And today, I'm going to continue the theme of measuring distances, because you will see how that leads not only to the figuring out of what the scale of the universe is, but also what makes up the universe, dark matter and dark energy. Now, I'm going to just mention how this is done, and this will be taken up in greater detail in later lectures. But my point is to just show how measuring of distance is very important. Right? But and I will stop from time to time to take questions, but please keep the questions relevant. Right. So today, if anybody's followed the news and or looked at my social media, you would find that today is in Pune, where I'm sitting. I know most of you are not here. It's Zero Shadow Day. Happens twice a year if you are in between the tropics. So if you live anywhere between these two lines of latitude, and it's 23.5 degrees north and 23.5 degrees south, now you can figure out why the 23.5 degrees came. Then there comes 2 days in which around midday, the sun is exactly overhead, and so nothing has a shadow. Now, if you live in Delhi, for example, or in North Bengal, or in UP, or in Himachal Pradesh, you will find that you won't get exactly that. But on that particular day, it is actually, if you go to any of these websites, we have links to show, given where you live, you can figure out when the Zero Shadow Day happens. And anywhere in India, if you're not within the tropics, you will get almost zero shadow, but not exactly. So today, exactly at 12:31 here, at that time, I will be doing this lecture, so I won't be able to go and see it. Maybe I can see it from my window. I will be able to see how shadows vanish. Why is that shadow vanish? Because the sun at that time will come exactly on top. Why is that? Because if you remember, here is the inclination of the orbit of the Earth to the orbit of the sun, and that is 23.5 degrees. And so, as you can easily see, that on one particular day, given this band here, there will be the sun will be directly overhead on one day. And if you're outside that band, because it's outside the 23.5 degree angle, then the sun will never exactly be overhead. From this diagram, you can make that out. Okay. So anyway, so this is a reference to what we did earlier on. And in Pune, it happens to be today and then again at July 30th. But where you are, it could have already happened one, but there's another coming after June. And so look out for it. It's great fun. You can put something out in the sun, and you can see that suddenly the shadows will vanish. And we can do all kinds of things. We put out things that have wires and various features, and you can see the shadow slowly coming and coming exactly under, and the shadow is very, very sharp. And underneath, if the light goes through, and if it's a vertical thing, then the shadow vanishes. Very nice. Thanks. Good Facebook opportunity. So today I was going to talk about how to extend this feature of the cosmological distance ladder. Right? And so we went to making direct measurements of the by bouncing light off and bouncing radio waves of planets and moon and things like that. That's a direct way. Then we went up to parallax, which is the nearby stars, where it's a geometrical method. So it's also a direct. It doesn't depend on any strict modeling, that is. But then that depends on the first rung of the ladder. And but then I also said that you can really do it for the nearest 1,000, 10,000 stars, and with the current satellites, the Hipparcos and then Gaia, we can actually go up to 1 billion stars, and that is halfway up to the expanse of the galaxy, our own galaxy. But as soon as you go outside the galaxy, this method does not work. Okay, because the things are so far away that they will not have a parallax, even if you send the satellite to the Lagrangian points far away from the Earth. Okay, so then you have to come up with some other method. And so I'm going to talk about the spectroscopic parallax, which is main sequence fitting, a little later. That will depend on your knowledge of the main sequence, something that Professor Dipankar Bhattacharya has been doing this week. So you should be familiar with the Hertzsprung-Russell diagram. And then next comes the other methods, which we call the standard candle methods. Now, what are the standard candle methods? The standard candle method is if you know how bright something is or how big something is, then from measuring the amount of light that's coming to you from that object, you can figure out how far away they are. Because light falls off as 1 over r squared. So the apparent luminosity of something is the absolute luminosity L divided by 4 pi r squared. And so that r is the distance. And so if you know L, capital L, which is how bright it is actually, so you take a 100-watt bulb and you know it actually 100 watts. You can measure it, and then you can send it far away, except that in the case of stars, you can't, you don't know. So there has to be some astronomical knowledge in which you should know how big something is. It works for big as well. So if you have a sign that you know it's really 1 meter big, then you place it at different distances on the road, and you look, and you'll figure out how far away they are. And looking at their apparent angle, you can find out the distance. I shared that small angle formula, which means that if you have the angle in radians, then r is equal to s theta or whatever, d equals alpha d, which is if you know the distance, if you know the size of something, then you measure the apparent size, and then you know the distance. So that's called a standard candle method, right? So you have to know then how bright a star is. How will you know that? And this is where the major breakthrough came at the beginning of the 20th century. Before that, this method could not be used, and this is why we couldn't go beyond parallax. And this is also why, at the beginning of the 20th century, remember, special relativity has been published, Planck's law has been published, the electron has been discovered, and yet we do not know whether the universe is kiloparsecs, megaparsecs, or gigaparsecs big. Right? This is a new concept, and so parallax doesn't work up to there. So let's see. So first of all, I said there is, before getting to the standard candle methods, in the stars of our galaxy, even if you do not have direct parallax measurement, there is a second order parallax method that you can use, and it's called a spectroscopic parallax. It's actually not a parallax method, and that depends on this concept. Okay, so I'm assuming everybody here now knows what the Hertzsprung-Russell diagram is. The Hertzsprung-Russell diagram is a relation between the luminosity of a star and its color. And the x-axis is a color, which is also a measure of the temperature, because stars are black bodies. And a black body, the temperature is completely dependent. Temperature defines its spectrum. And from the spectrum, a color is essentially the ratio of its luminosity at two different frequencies. That's what a color is. And that will be fixed. So color will be fixed. And then, the spectral type comes from applying then the Mignan-Saha equation, the Saha equation, to this concept, and then you can find the spectral type. So the spectral type is the same as the temperature on top. If you look at the top, you can see the surface temperature of the star, and our sun is 6,000 degrees, 5,800 actually. So there you are, that's our sun there, and you can see the luminosity of that is 1. It's plotted here in log scale, but to the ratio to the luminosity of the sun. The sun's luminosity, whatever it is, 4 times 10, 6, forget now, is the luminosity of the sun. And that, and then you take the ratio, 100, 10,000, etc., etc. And so this is log scale. This also is on a log scale, as you can see, log of temperature. And then you have this very nice relation called the main sequence. And the main sequence is where the star spends most of its lifetime, and that is when it is burning nuclear fuel, doing nuclear fusion in its core. Now, as soon as doing the basic nuclear fusion in its core, which is burning hydrogen into helium, finishes, the star starts going off the main sequence in this particular diagram, because the relation between the luminosity and the temperature changes. It is no longer just a black body, but other things are happening in the star, right? But when it's in hydrostatic equilibrium, burning nuclear fuel as a black body and radiating it as a black body from the surface, and in the core burning nuclear fuel, the whole thing is in equilibrium, then it is on the main sequence. So how do you use that to measure distance? What you do is here, because on the main sequence, the star's luminosity and color are related, and color is something that you can measure. You can take 2 filters, take the picture of a star in 2 filters, and take the ratio of the 2 fluxes. That exactly tells you what the temperature of the star is and the color of the star is, right? Because it's a black body. Black body temperature defines the Planck spectrum, and so that can be measured from the Earth. That is not distance dependent, right? You have to do some color correction because of the color change as the light comes through the atmosphere, but that is very well known. We know how to do that. Okay. So how can you measure distance? So I told you it's a standard candle method. Standard candle means you have to find cleverly, and if any of you find the standard candle method, you just become instantly famous. And as you will see, one of these groups who found a great standard candle method even got the Nobel Prize, right? So the standard candle method here says that if you can measure the color of a star, that tells you what its luminosity is, if it's on the main sequence, that is. So you have to first establish the star is on the main sequence. You have to place it on this plot. And then once you do that, then if you know the luminosity, then because you can measure its flux using a small photometer along with a telescope, then you know that the flux is luminosity divided by 4 pi r squared, and you know the distance. Okay, so if you know what the actual power output of the star is, which is given by the y-axis here, you can use it. And it's good to tens of kiloparsecs because it's good within our galaxy, really, because you can't resolve stars in other galaxies very well, and it really works very well to this kind of accuracy within our galaxy. This is known as spectroscopic parallax for a very strange reason. There is no parallax involved in it, right? But maybe because it was spectroscopic. Why spectroscopic? You don't need a spectrum of a star, you just need a color. But it has, color gives you some spectral information, right? So people, I think, use this along with the parallax, because actually the HR diagram is calibrated with parallax, right? It is calibrated, this whole thing is calibrated with some stars for which we know the parallax and so know how far away it is, and that is how you fix this. And so it is known as spectroscopic parallax. Okay, so that's this. And then now with Hipparcos and now with Gaia, and I didn't put the Gaia one, it's so good, but that's emerging science, people are doing it with Gaia. But this one, Hipparcos, 100,000 stars, because the parallax was measured so well for all these stars, these are all the stars with known distances. So you can see how nicely you can take out the main sequence, and then once the main sequence is known, you can place something, other stars on this to figure out what their luminosity is. And here it says absolute visual magnitude, but it's just the way astronomers call luminosity, minus 2.5 log of luminosity. And here, as you can see, it's a color index, temperature, etc. The caveat here is, and this is why it is hard to use this to make it very, very accurate distance. But you can easily say it's kiloparsecs or tens of kiloparsecs, right? And so this is, as you can see, you can use this to figure out the scale of the universe, but measuring distances accurately to individual stars is limited by the fact that this main sequence is not as thin as I showed you here. This is Hipparcos with very accurately measured parallax distances, and you can see this one is pretty thick. And so the range, if you know the color, and you want to place the star here, then there is a big spread, a big error. And that error then will be the error in the luminosity. And then that will translate into the error in the distance. Okay, so that's some. Right, so these are essentially the beginning of the standard candles. But the main, as I said, and I'll take questions in a little while, main breakthrough came when this happened. At the beginning of the 20th century, in 1910s or so, Henrietta Leavitt, one of the most distinguished astronomers in the 20th century, Henrietta Leavitt was working at the Harvard Observatory at a time when women were not allowed to actually get university degrees in Oxford, Cambridge, Harvard, places like that. Even in India, though in India, women started getting university degrees a little earlier because the British experimented in India first before starting it in their country. In Oxford, when did the university? In Oxford, 1920, I think, was the first women degrees. So in Harvard was the same, and so there was a bunch of women who worked here. Here they are at Radcliffe College, which was under Harvard University, just opposite the Center for Astrophysics, where I had worked for many years. The Center for Astrophysics, at that time, Pickering was in charge of the lab, and he had undergraduates from Radcliffe College, women who were allowed to register for Harvard University but not get a degree or sit for exams. They were working the most at that time. And what they were doing is they were looking at photographs of the sky and trying to discover things about the universe, about our galaxy. And Henrietta Leavitt was a leader of a team that found this amazing relation just by looking at and measuring the blackness or grayness of stars on photographic plates and measuring their intensities. And she found this amazing effect where she found that there is a certain kind of variables which you can identify by their spectroscopic properties, but also by where they live in the galaxy and things like that. And they have a very characteristic sinusoidal variation. And these things vary over days. Actually, in one evening, in one of the universities I taught, I had an experiment that second-year undergraduates did. where even in one evening, starting from 8 o'clock to 12, you sit and plot the luminosity of a Cepheid variable, and it varied enough that you could fit a sinusoidal curve to it. Normally 3-5 days, something like that is the total period. And then the Cepheid variable is a star that is actually off the main sequence. It is gone off the main sequence. It just got unstable. So these things are pulsating. And as they pulsate, as they grow big, then their magnitude, their luminosity changes, and then they grow small, etc., etc. And so this pulsation happens, and the rate of pulsation, which is given in this light curve, is related to their luminosity, the absolute luminosity, the actual output of the star, the mass of the star, as well as the luminosity. So then this is something that you can measure, right? You can measure how this Cepheid variable is pulsating, and once you can measure that, then you can find its absolute magnitude. And once you find its absolute magnitude or absolute luminosity, you know how far away it is. So Henry de Leavitt had this amazing discovery. Now, Cepheid variables, this is where actually, I think this is shifted a bit. Cepheid variables are out there in the main sequence. There are some Cepheid variable light curves which are not that simple. They're not completely sinusoidal, depending upon the star itself, but you can see that their period in days can be as small as 3 or 5 days and as big as 15 days a month, etc. But you can see there's a lot of variation, and the variation depends on the mass, because that's how the oscillation works. And so and I will show you how Hubble came to first measure the scale of the universe. And Hubble used this in the 1930s, this particular method to locate Cepheid variables, first in our galaxy and then in other galaxies. If you can resolve and find these variable stars in nearby galaxies, then you get by the rate of pulsation, you can figure out how bright they are and so how far away they are. Okay, right. So I'm going to, because I am short for time today, I'm going to take a couple of questions. In my list here, I have first Varsha Gautam has asked a question. Please ask your question. I'm unmuted you, Varsha.
Hello, sir.
Yes, go ahead.
Sir, the luminosity is the reason why stars don't appear green or purple.
I don't understand. Luminosity has nothing to do with color. Luminosity is the total energy output from a star.
But
brightness has nothing to do with color. Yeah.
But I think in slide number 121, this is mentioned that luminosity and colors are related.
Yeah, but that's the whole HR diagram, right? The HR diagram shows that the luminosity and color have this relation if you're on the main sequence, but not for all stars. So for a black body, think about it. A black body, you know some basic relations. A black body tells you that its spectrum is fixed, right?
Yes.
So its color will be related to its temperature. And for a black body, you also know the Stefan-Boltzmann law, which tells you that the luminosity is proportional to T to the power 4. But in the proportionality constant, there's also the size of the star area. Okay? So you can see how the luminosity is related to temperature and temperature is related to color. But only if it's a black body and only if it's in equilibrium, and so it's on the mean sequence. Okay. And the relation between luminosity and color is used to find the distance. That's all I'm saying. But only if it's on the main sequence. Okay? Right. I hope that makes it clear. I'll take only one more question. I'm sorry. I'm going to go to Soham Kapadia, which is the next one. Go ahead. Yes, Soham, go away.
Hello, sir.
Yes.
Sir, you said that the limiting factor of accurately finding the distance is the thickness. The thickness is like, it is not very sharp. But what for those, like the right part of this diagram where there are two arms? So what luminosity do we guess? Like there are two arms, right? On the right part of the diagram.
You're talking of these ones. No, you can't. You can only get the distance if they are main sequence stars. Because otherwise, anywhere else in the diagram, there is no simple relation between the luminosity and the temperature. So you can't take the temperature and you can't find this. No, right? Because it's not defined. But main sequence stars, you can actually find their main sequence or not by many other means. Partly because they are very stable, and they from its spectrum and things like that, you can even identify whether they're main sequence or not. If they're a red giant, you will know it's a red giant. If there's a blue giant, you know it's a blue giant, etc., etc. But main sequence stars are sun-like stars, which can be identified, and then from it you can measure the distance. That's all I'm saying. Okay. I'm sorry, I'm not going to take any more questions now. I'm in the chat box. There are a couple of things I'll just quickly go through. Ishika is saying that is the pulsating brightness graph, is it apparent or actual brightness? It's actually the same because it's at a distance. You don't, from the Earth, measure the actual brightness. You don't know what it is. So you measure the apparent brightness. And then from the apparent brightness and the pulsation period, you know what its actual brightness is, right? Because the pulsation period gives you the actual brightness. You have measured the apparent brightness, and from the two you can measure the distance. That's the whole point. So here, this is the brightness, which is the apparent brightness that you can measure from the Earth. That the mean brightness of that will tell you what the mean brightness of it, flux of it from the Earth is. Then the period will tell you what the actual brightness is, and from the ratio of the two, you can get the distance. Neil is asking, what is the difference between B minus V color and the V minus I color? It's very simple. You use different filters. I don't know whether anybody's going to teach you observational astronomy. B, V, R, I. These are broadband filters with about 100 nanometers width, and B is of course centered around 400 nanometers. V is centered around 550 nanometers and stuff like that. And these filters essentially give you the flux of a certain thing through that filter. So and R is centered around 650 or something like that. And so, for example, and I is a little more. So a B minus V color, it's called a color because it's just the ratio of the fluxes of the two at the two filters. So something that is blue will give you more in blue and less in V. Something that is red will give you more in R and less in V. And so the ratio tells you what the color is. That's why it's called a color. And so if it's a single black body, then B minus V and V minus I are related, right? But if it's two different stars, one's a blue star and one's a red star, then the V minus V I or the V minus V tells you what its color is. Okay, right. What is the physical process of the pulsation of the Cepheid variables? It's a very interesting question, and I hope somebody talks about it in the stellar lectures. And that is once the equilibrium between the gravitational force and the thermal motion due to the heat that's being produced in the star, the balance is lost, then the star goes out of equilibrium, and then they start pulsating radially. And the radial pulsations is a subject of its own. It's a fantastic subject. There are many kinds of radial pulsations. Stars, when they're on the main sequence, also pulsate. This is called heliosismology, for example, for the sun, or asterosismology for stars. And they're small little pulsations because they're always hovering around that equilibrium period. But these oscillations become very, very large when they're out of equilibrium. It's a lovely, very, very interesting subject. Okay, so I will move because I've got two more things to cover today. And I just wanted to tell you that the Hubble Space Telescope was launched in 1990, was essentially because of this, to find Cepheid variables in other galaxies. That was its main goal. It was called Hubble, because it was Hubble who first in 1930, and I'll talk about it in a minute, Hubble was first used Cepheid variables to measure distances to galaxies. But he found that he could only do it to the nearby galaxies up to about 5-6 megaparsecs, and that's it. Then you couldn't find the resolution to find individual stars in other galaxies. it was felt that if we have a digital camera, remember that's how the digital camera was developed, the ones you have in your pocket, and on a space telescope, which will have better resolution if it's above the atmosphere, then you can find Cepheid variables out to 20 megaparsecs, the Virgo cluster and beyond, and that's exactly what was done, right? And the first thing that the Hubble Space Telescope did in its first few years was find Cepheid variables in external galaxies as a key project. This was guaranteed time, and then that kind of helped settle the Hubble constant and the distance scale. So this is one of the key things that happened. And you can see these are the early pictures of the Cepheid variables that the Hubble Space Telescope found. Don't worry about these. We'll talk about these later on in the course. But we know that the Hubble constant that came out of that is about 72 kilometers per second per megaparsec, and I'll talk about it in a minute. So this led to this belief that Hubble's law, which we talk about, Hubble's law, Hubble found what Edwin Hubble did. Hubble was a very interesting character. He was a lawyer who practiced in Chicago, and then when the First World War started, he went to fight in France for the American army, and he lay in the trenches, looked up at the sky for days and nights, and then realized that he was in the wrong profession. He wanted to do astronomy. So in his 30s, he came back after the end of the war and joined the University of Chicago to study astronomy. So it just shows that people can do this even very later in life, and astronomy is full of such characters. Once he finished his degree, he was in his mid-30s. He then found his first assignment at Mount Wilson Observatory in California, where he was working with a 100-inch telescope, then the largest telescope in the world, with a spectrograph. It's the first big spectrograph that was installed on a major telescope. And he essentially put the spectrograph together on the telescope, and the first assignment he gave himself was to take spectra of these fuzzy objects in the sky that Herschel and Messier had identified. That is one of the reasons why I started off talking about them with Herschel's list and Messier's list, because in 1920 it is still unresolved, this issue, whether the fuzzy objects, the nebulous objects, are actually stars or not, right? And so Hubble thought that in looking at the spectra of these objects, you can identify what these things are, you can know what these things are much better. By that time, already, it was known that the universe is pretty old. Age of the universe has always been another problem, because Newton believed, for example, the universe is 4,000 years old. And that was based on some measurement made from the Bible. Various incidents in the Bible were dated according to how what happened, etc. And scholars then said that maybe it's about 4,000 years old. Newton actually wrote a whole book claiming that it was 4,000 years old. But when it came to the 19th century, people realized that the universe had to be much, much older than that. And when Darwin published his theory of evolution, it was very clear that you cannot have evolution in 5,000 years or 4,000 years. And it was very clear you needed millions, hundreds of millions of years, maybe billions of years to actually have this kind of evolution. And that had a big clash with the religious people who believed that things were 4,000 years old. And so throughout the 19th century, there was this whole thing about measuring the age of the Earth. Remember, radioactivity had not been discovered yet. And people tried to date the fossils that were found and trying to figure out how long it takes for rocks to build up. And it was clear by about 1850 that the Earth was at least about 500,000 years old, maybe 200,000, 300,000 years old. And that didn't satisfy Darwin's criteria. Okay, and then comes the next stage in the beginning of the 20th century. And because we know, and then people realized that this Einstein's general relativity theory essentially suggested that the universe is expanding. And all that will be covered in cosmology. I'm not going to talk about that. But if the universe is expanding, then you realize that if you measure the expansion rate of the universe, then you can figure out how old the universe is by extrapolating backwards. This thing that we call the Hubble constant is actually the rate of expansion, current rate of expansion of the universe. And it's expressed in this funny unit called kilometers per second per megaparsec. But it's actually because it comes from this formula. What Hubble did was Hubble looked at the spectra of different galaxies, and what he was doing was that he was Hubble was worked with this man called Milton Humason, who actually was, again, a very interesting person. He was not a physicist at all. He was actually a mule driver who helped carry the mirror of this telescope up the mountains when the telescope was being established, and then worked as a technician with the telescope. So Humason and Hubble together put this thing, the spectrograph on this telescope together. You can see this, the 100-inch telescope, and started measuring the spectra of different nebulae. And the point is that, and by this time you must know the basic thing of measuring velocities in astronomy, and that is that in a spectrum of all objects, stars or galaxies, you have these emission or absorption lines. And if something is moving with respect to you in a radial direction, then if they're moving away from you, the lines are red shifted, which means they're shifted towards the right because of Doppler shift. If it's coming towards you, it is blue shifted, which is going to the blue side. And you can see that if this is the spectrum of a particular black body on the Earth with a certain lines on it due to various chemical elements, then what will happen is that you will find them red shifted if they're moving away from you. So this is what, to his surprise, Hubble found as he measured the spectra of different things, and he found that for all the things that he measured, and this is from Hubble's original paper in the beginning in 1929, after he'd done all this, what he'd done was he'd found Cepheid variables in some of the nearby galaxies around us. We didn't know there were galaxies then. In the nebulous objects in the list of Herschel, and many of them turned out to be distance, and then he measured the distance with Cepheid variables, and many of them turned out to be very, very close. They're in our galaxy, because we didn't know whether our galaxy was a galaxy then, and he found that many of them were millions of light years away, and he found that almost all of them were going away from us. Only these three objects are coming towards us. 1, 2, 3 have negative velocities, which means that they are coming towards us. They are blue shifted, and all the others are red shifted. And from this, he came to this amazing conclusion that if we look at all galaxies and most of them are going away from us, then it is telling us something. If, for example, we were all in thermal motion, all galaxies in the universe, then there will be equal number of red shifts and blue shifts. And in this case, he saw that most of them are going away from us. And so he came to the conclusion that actually the universe is expanding. It so happened that in 1915, Einstein had published his theory of relativity, general relativity, and from the first people who had solved those equations, Lemaitre and Friedman and people like that independently had shown that the universe cannot be static. It could either expand or contract, and you'll hear all about it later on in the cosmology lectures. And then Hubble's findings found a resonance there. People who were saying, look, if the universe is expanding, you should see that all galaxies are moving away from each other. Now, you can see Hubble's plot. Now, if my student doing a project with me actually has a plot like this and draws a straight line through it, I will throw the thing away. It is really an awful fit. But this is the most famous plot in cosmology. right? It worked. He actually did it in 1929, and it turns out that it was actually quite a good thing. And from this, he could write this relation V is proportional to, V, which is here, is proportional to distance, and the constant of proportionality is the rate of expansion of the universe, which is expressed, as I said, in kilometers per second per megaparsec. He also found, because his calibration of the Cepheids were all wrong, his value was 500 kilometers per second per megaparsec, and that gave, if you take the inverse of that, gives you the age of the universe, gave the age of the universe to be about 2 billion years, which already was smaller than the measured age of the Earth by then. By then, radioactive dating of carbon dating of rocks had happened, and it was already showing that the Earth and the Sun were more than 4 gigayears old, and Hubble already showed that the universe was 2 gigayears old, which is impossible. So but it is the first time in an astronomical sense, gigayears had come into the picture. So this was a very interesting phase, and now we know that from the Cepheid variables that are found by the Hubble Space Telescope in the 90s, it came down to 72. But you can see that you can initially, if you do a very famous experiment, you can get it wrong. So here was Hubble's plot, and here is the same plot from the 1990s. Okay, after the Hubble Space Telescope went up. Now, if you look here, you're going to millions of light years. Here, you're going to hundreds of millions of light years, and that yellow spot is where all these galaxies would be. Right, so you can see that this whole standard candle method has been pushed quite a lot in the entire 20th century, and you can also see that the scatter is very small. You actually have a straight line that goes through these that give you the expansion of the universe, and the slope of this line gives you the Hubble constant, which is the rate of expansion of the universe in kilometers per second per megaparsec. So the dimension of that quantity is 1 over time. Kilometers megaparsecs cancel. 1 over time, and if you take the inverse of that, that becomes the age of the universe, or related to the age of the universe. Then the question comes, how far away from us is this valid? So here is my question. I am on the Earth, and I'm looking out into the universe, and in our galaxy, looking out at the universe now, and I'm measuring the rate of expansion of the universe from now, right? And that's why it's called the Hubble constant. The Hubble constant cannot be constant. Think about this. If the universe is full of matter, and the universe started off with a bang, the gravitational force of the entire matter would pull it back. So just like you throw something up in the air, it decelerates. It gets to a point, and then it comes down again, right? And why is it decelerating? Because it's the collective gravity of the Earth that is pulling it back. So now the collective mass, the gravity due to all the matter in the universe, is going to pull back the universe, even if it started with a bang, right? And so your expectation is that as the universe expands, it's going to decelerate, which means it's going to slow down and stop and come back again. And this is what Hawking wrote in his famous book in the 1980s, The Brief History of Time. And I remember I was a student then in Cambridge, and I attended his lectures, which became the book. The lectures called The Short History of Time. And he spent almost all of the lectures, as well as the book, on how, depending on how much matter there is in the universe, this slowing down of the universe and coming back again is going to be determined. And this is why it's most important to find how much matter there is in the universe. So look at this diagram, and if you're looking further and further away, I told you when you look further and further away in the universe, you're looking into the past of the universe, right? So if you find galaxies that are very far away, you can look at a phase of the universe that is in the past, and the universe is decelerating. Then the universe would have been expanding faster in the past. So the slope of this curve is going to go steepen in the past, so it will go up So it will be steeper in the past or further away from us. So how far away is this V equals H naught D valid? It should not be. It should actually be much steeper in the past if the universe is decelerating. And this is where our thing happened. I'm going to skip a lot of what I have next because I'm losing time. And I'll come to here, where we are. So we are here, as I said, the 1929 data fit there, and this is the time from 1995. And we were stuck because we could not really go any further and measure the expansion rate of the universe because we did not have a distance indicator, a standard candle distance indicator that could take us beyond the nearest few light year megaparsecs. The Cepheid variables work till about 20-25 megaparsecs. Then, based on that, there are some secondary distance indicators which I didn't talk about, calibrated on the Cepheid variables that take out to about 100 megaparsecs or so, and things like that. But really, you can see that there aren't many galaxies beyond about 200 megaparsecs, 600 light years at that time that one could, and even then, out to that distance, this line is very flat. Okay. So then came 1995, the great discovery, which got the Nobel Prize. And that is the discovery of a standard candle, which is the which is the white dwarf supernovae. So what happens is that there's a type, it's a type of supernova called the type 1a supernova. And this supernova is, of course, most supernovae, as you know already from Dipankar Bhattacharya's lectures, are stars that explode at the end of massive stars that explode at the end of their nuclear burning life. But there is a class of supernovae called type 1a supernovae, which we now know are essentially stars that explode. So in the case of the normal supernovae, the type 1 and type 2 supernovae that Dipankar Bhattacharya would have talked about, so at the end of its life, a massive star would explode such that the outer layers explode and the inner part implodes to form a compact object, a white dwarf or a neutron star or a black hole. So there's the ratio between how much is exploded and how much is left behind is variable from star to star. In the case of a type 1a supernova, what happens is that it's actually a white dwarf on which accreting matter from its companion, and suddenly, if too much matter falls on the white dwarf, it becomes very unstable, and it explodes. And in this case, the whole star explodes. And so there is no relation between how much explodes and how much doesn't. And so you can intuitively see that a whole star exploding, the amount of energy that's released is related to the mass of the star, and white dwarfs have, courtesy of Chandrasekhar, the Chandrasekhar equation, the same mass, essentially. So this is why it becomes a standard candle. A supernova type 1a magnitude, a maximum absolute magnitude, is fixed. This is what we discovered in 95, and it becomes a standard candle. And supernovae are so bright, they can be seen very far away, very, very, very far away in distant galaxies, which normal stars can't. So this is what changed the game completely in this distance game. And you can see this is a famous example of a type 1a supernova. It happened in the Large Magellanic Cloud, which is one of our satellite galaxies nearby, in 1987, and was seen with the naked eye by two people, one in Chile and one in Australia. Just looking up at the sky, they said, "Look, that star wasn't there yesterday." So then people followed up and figured out that was a supernova. This is the nearest supernova that has been seen in the last 300 years. And that was a type 1a supernova. I discovered a type 1a supernova in my very first observing run as in a telescope in Chile as a PhD student. But at that time in 1990, I think, 91. Yeah, so it must have been just after I finished my PhD. And 91, it was in March, and it was already the 20th supernova discovered that year. So it is not, it wasn't a very unusual thing then. But of course, finding a supernova in our galaxy is very different. These are supernovae you're finding in other galaxies. So it becomes a standard candle because once you find something like this and you can establish it's a type 1a supernovae. So this is the scenario. I already told you about it, that matter falls on a white dwarf and it explodes. I'm not going to go into it. So the light curve of a type 1a supernova looks like this. So it reaches a maximum, and the width of this actually has a dependence on the peak luminosity. I'm not going to go on it, but you have to fit a model to it and find out exactly where the peak occurs. So you have to find the supernova at a time before it reaches its peak, because it's the peak that defines how far away it is. Okay? So they have now become standard candles, and if you find one, you find the distance to the supernova, and since it's an external galaxy, you find the distance to the galaxy. So that's the idea. You actually know you have to find it where the peak is. So once this was discovered in '95, it became a common practice for telescopes to do supernova surveys. So there are some telescopes even now that are dedicated to do just supernova surveys. In fact, the 4-meter telescope that I showed you in that picture of the Milky Way from Chile, that is called the Dark Energy Telescope now, and it does exclusively supernova search. And what it does is, it takes pictures of parts of the sky, maybe 200, 300 parts of the sky, every night, and goes back to the same part the next night, and the next night, and the next night, and the next night, and next night, and takes multicolored images. And digitally then subtracts one image from the other, and then finds what has changed. And in some cases, it would be some satellite. In fact, with Elon Musk's new Starlink program, this has become a pain in our heads. Astronomy will probably be destroyed because of this, because those are the things that appear. There are hundreds of them up there, and they appear, and we have to take them out and stuff like that. But automatically, you can find what has changed. And this is the telescope, if you remember, I showed you on Chile. That is one of these telescopes that does this as a matter of routine. And then once you subtract this from that, you can find that supernova if it's happened, right? And as soon as those things are discovered, then you go and notify the bigger telescopes, the Hubble Space Telescope and things like that. They take a spectrum, and the spectrum tells you whether it's a type 1a or a type 2 supernova. Because in type 2 supernova, you can see iron lines and much higher lines in the periodic table. A carbon-oxygen white dwarf exploding into a type 1a supernova, they don't have anything higher than oxygen and nitrogen in the periodic table, only elements from hydrogen to oxygen. And so they can essentially tell you whether it's a type 1a supernova or a much more advanced supernova. And once you have a type 1a supernova, you're sure that that's a standard candle. And now we are actually discovering hundreds of these supernovae every year. And so that's, if you remember, Hubble's plot in 1995, and we asked the question, where is this going to go, and how is that speed going to change? With the first few of these supernovae that helped us find distances to galaxies that are very far away, much further than 500 megaparsecs, this is what was found. So this is a plot, and here, if you remember your 1929 data fit in that yellow thing, this is within the first 5 years. This is a plot I'm showing from about 2001 or so. Already, that entire last plot has fit into this little yellow blob. And as I said, we expected in the past the H naught to be steepening, because the universe must have been expanding faster in the past and decelerating. And the biggest surprise, and this is what led to the Nobel Prize, was that we found that the universe was much slower in the past. You can see the slope in the farther away from us is actually flattening. So the slope is much smaller, and this means the universe is accelerating. This, was not expected anywhere. It was not in Hawking's book, The Brief History of Time. People didn't think that we would find a component of the universe that is going to be something that doesn't decelerate because all gravitating matter pulls back. And here, this shows that the universe is made up of something that doesn't pull back but actually pushes. So it's not gravity. The universe is made up of mostly of matter that does not do what gravity does, what matter does, and doesn't pull back. It's actually pushing things away, and the universe is accelerating. And this is now called dark energy. So supernovae essentially found that that universes. So you will find in the rest of the lectures later on what dark matter is, and you'll find that we know that most of matter in the universe is in the form of dark matter. But we now know that if you look at the entire I've seen before Planck and after Planck. Planck is the cosmic microwave background satellite that you hear about. From that, we know that if you take the entire mass energy budget of the universe equals mc squared, the mass energy is the same, then only about 30% of the universe is made up of matter, and you can see that most of it's dark matter, and the rest of it's ordinary matter. Ordinary matter means matter that is made up of baryons, protons and neutrons, actually made up of quarks, and so things that we are made of, our periodic table is made of. It's only 5% of the universe. So you see how we've come in the history of astronomy, how far away. First of all, thinking that everything moved around the Earth, that humans are the best species in the universe, and everything. Now we know that all that we are familiar with in our daily lives that come from the periodic table elements, whose nucleus is made up of quarks, actually makes up 5% of the entire universe. The rest of it, the rest of the matter is 5 times that, and that is made up of something that is not made of quarks. And actually 70% of the energy of the universe is in a form that doesn't even gravitate. It is actually pushing the universe away. And so what I will do is I'll stop there, and I will take some questions and look at the chat box for some questions. And let's see who is there. I did go to Soham Kapadia, didn't I? Soham, did you ask your question?
Yeah, sorry, sir. Sorry, I forgot to load.
Junik, you're next.
Hello, sir. Good morning.
Good morning.
Thank you for the lecture. Sir, my question is there any possibility that the Cepheid variables came back to their stable state after a long time, or does they do that?
No, when a star gets to a Cepheid variable stage, it is already unstable. And there's nothing that can bring it back to stability again. Because while a star is on the main sequence, its hydrostatic equilibrium means that the thermal motion of the plasma in the star actually is balanced by the gravitational force. And in more massive stars, there's a third component, and that is the radiation pressure of the radiation that's coming out from the center of the star. And all these things are in equilibrium. Once that central cooking facility in the star, which is the nuclear fusion, stops, then all this goes out of equilibrium. And then a lot of non-equilibrium things start happening, and one of them is these oscillations. And there's nothing that restores it. And so at the end of the Cepheid variable stage, what will happen is that the star will start losing its matter, and then eventually it will either lose its shell and shrink down, the core will shrink down to become a white dwarf, or the outer parts of the star will blow up in a supernova. And that happens a little bit after the Cepheid variable stage. But and not all stars go through a Cepheid variable stage. The various parts of the HR diagram in which stars, depending on their mass, go through, and that is outside the scope of my lecture. I'm sure some of it has been already done by the Pankaj Bhattacharya. So I'll stop there and go to Radhika's question.
Thank you, sir.
Radhika Deshmukh. Can you hear me? Okay, now I've unmuted you. Not seem to unmute you. Okay, so let's move on. Let's go to Kaushik Manjo. Kaushik, I've unmuted you.
Yes, thank you, sir. Hello, sir. Am I audible to you?
Yes. Go ahead. Yeah.
Yes, sir, thank you, sir, for your lecture. It was just awesome. Sir, I have a question. It's a kind of apparent question. Sir, as we look into the night sky and when the Orion constellation rises, in the feet of the Orion constellation, we see the regal star that is quite bright in color and one of the most brightest star in the night sky. And moreover, it changes its color. But in the shoulder of the Orion, there is the Betelgeuse, but it doesn't change. It's a kind of red giant. Why? What is the difference between this?
And no, I don't think Rigel's color changes. Its color is the same. Yeah, how can a star's color change while you're looking at it? Stars' colors thousands of years or even millions of years for the colors to change. It can change because of various local effects or the atmospheric effects. But you're right, Rigel's color is different from Betelgeuse. Betelgeuse is a red giant. And it's actually very close to going supernova. As you know, we are waiting for Betelgeuse. It can any day go supernova. Some people predicted even now it can go supernova. Some people are predicting maybe it'll take a few hundred years. So it is in the last phase of the red giant phase, and it's really, really very, very big and red. And its outer surface is very cold, which is why it's red. And so this is what happens. So as the star expands, the outer surface becomes very big, but also its temperature drops because something is expanding adiabatically. So its surface temperature is extremely low, and it becomes red. So red giants are like that. So Betelgeuse is one of those. Whereas Rigel is in a different part of the HR diagram, and so its color is different.
So why, sir, this local effect doesn't act on the color of red giant? I mean, on the Betelgeuse.
No, I'm not sure how you think that as you're looking at Rigel, its color changes in the evening. That's not true.
Okay,
that is not true. I mean, go look at some other effect that's happening while you're observing it, because stars' colors cannot change visually while you're looking at them. Of the over hours, that is. It normally takes years or hundreds of years, thousands of years, things like that. Okay. So look up Rigel and see what its properties are.
Okay. Thank you. Okay.
Next question is Elanbaum Samananda. Yes. I'm trying to unmute you. See if you can unmute yourself. Yeah, go ahead.
Trial version.
Go ahead with your question.
Trial version.
Okay, so clearly we can't do it. So
trial version. Trial version.
Okay, Shorab Pal is next. Shorab, I've unmuted you.
Okay.
Go ahead.
Am I audible?
Yes.
Sir, is it possible to determine, depending upon the data we have, how long our universe will expand?
Well, now I told you the universe is accelerating. So
yeah.
So
before it decelerates.
Before no, but Hawking's idea was the universe is going to come back, and then you can talk about a finite time for the universe to expand. Now the universe is going to expand forever.
Due to the dark currents.
Yeah. Because it's dark energy is actually, it turns out, I haven't told you the whole story, but you'll hear the whole story later on when people talk about this in cosmology. It turns out the dark energy phase, the accelerating phase, only started about halfway into the age of the universe. And initially the universe is decelerating. We now know that because we have now got to the phase of measuring distances to galaxies that are very far away. Then you can actually map out the expansion of the universe. And then there was a phase in the universe about halfway into the age of the universe when dark energy started dominating over matter. And now it completely dominates. And so in the future, that's going to dominate. And so the universe is just going to become a very large place, a very cold, and all the galaxies will be far away from each other and stuff like that in the future. In any case, we're not going to live that long. But yeah, so there is no point in talking about the future of the universe in terms of a finite age. It's just going to expand. Okay, Adarsh Pandey is next. Others shout on you.
I'm audible?
Yeah.
Sir,
Yeah.
my question is, sir, why Doppler effect is only accounted for the change in wavelength of light received from galaxy and not the other factors like tired light or Compton effect?
Okay, tired light is not a phenomenon that is actually accepted in physics anymore. People suggested such things long time ago, and it's not a very scientific thing. Go read up on what people think. Compton effect, etc. Those are things that happen in. Those are essentially phenomena, quantum phenomena that happen for photons when they encounter matter, electrons, protons, or whatever, or other photons. Here, you're looking at just the simple Doppler effect, where the whole spectrum shifts and the lines shift as well. If you're looking at the Compton effect, the whole spectrum is not going to do anything. Yeah, and the lines are not going to do anything. You can get one or two lines as a result of the Compton effect. If you're looking at the effect on a very local scale of photons encountering matter, right? And normally, in the Compton, in the inverse Compton effect and stuff like that, that Dipanjan has talked about, you see them in the spectrum of objects, particular objects that you know has a high energy thing going on or something. Here you're looking at a very simple thing that is moving, and the entire spectrum moves, all the lines move. No new line is being created, right? Which is what happens in all the other effects. And as a result,
So maybe the gravitational redshift occurs.
Yes, but to have a gravitational redshift of that magnitude, you need a mass that will need a black hole of the mass of a galaxy or something like that. You can convert gravitational redshift into mass. And gravitational redshift you do see. You see gravitational Doppler shifts near a black hole. And one of the things that, if you read some of the papers of the people who got the Nobel Prize this year, you will find that they have detected the gravitational redshift near in the spectra of the stars near the black hole in the middle of our galaxy. That's possible, but it's not possible on an intergalactic scale, because then to have this kind, you're talking of shifts of a line that is at 400 nanometers and is being shifted to 1000 nanometers, right? This kind of gravitational shift, if you put it in the equations that of the gravitational redshift, you will see that it requires the entire galaxy to be a black hole, or a cluster of galaxies to be a black hole. Those things don't exist. Right. Let me go to the next question, Anjali. Anjali, can you? I'm unmuting you. Go ahead.
Sir, am I audible?
Yes.
Sir, my question was regarding the white dwarf star supernova that we are using as the standard candles. So, since they have a constant mass of 1.44 solar masses, so similarly, neutron stars, their supernova should also have a constant mass around 3, I think, solar masses.
Yeah, but we don't have neutron star supernova. We have white dwarf supernova.
Yeah,
that is because mass falling on a white dwarf gets turned into a neutron star, and in that process, some loss of equilibrium happens, and it gets explodes into a supernova. We haven't found any. First of all, you also have to know that there is a spread in neutron star masses. They are not all 1.4 solar masses. It depends on their angular momentum, etc. But if, for example, the same thing happened to a neutron star and matter fell on the neutron star and the neutron star exploded, that's called a gamma ray burst.
Yes, sir. So like
17 event. They're very different phenomena. Their gamma rays and X-rays are emitted, not the kind of supernova that we're talking about. It's not a supernova, it's called a hypernova and stuff like that. And there, nobody's found a relation yet between. First of all, it doesn't emit light as much as it emits gamma rays and X-rays, because most of the energy that comes out of such a phenomenon comes out in high energy, because neutron stars are very compact, and they are the resultant phenomena actually emits a lot more X-rays and gamma rays and stuff. Nobody's found any utility in a standard candle business yet, but maybe you will. Maybe somebody will, and then we can use them as standard candles later on. But these type 1a supernovae are essentially white dwarfs that are exploding.
Okay, sir. So that was actually like I was wondering, because in 2017 we had a major event which LIGO and Virgo detected a neutron star merger in NGC. Like, since by now you told that we have to detect the peak. So by now, if Virgo can detect the collision, then we can easily be able to know when the peak will occur, right?
But you understand that, right? I mean, so you remember that was called a kilonova. So thanks
Yes.
for remembering that. And since then we have found another one, but we haven't found its optical counterpart. Right. So remember that Virgo or LIGO finds only the gravitational waves from when the merger happens. It's never gone and found anything after that. It's merged. Two neutron stars have merged into a black hole. Now, what is going to emit gravitational waves after that? Right? This is not matter falling slowly onto a white dwarf and making it explode. This is two neutron stars have merged to form a black hole. Now everything is a black hole after that. Nothing's coming out of it. So we are not actually measuring a light curve. We're measuring a very short burst of gravitational waves from a phenomenon. So there's nothing to use in this kind of a sense. Right? It would be wonderful if one can do that. Now, you're right that the 2017 event actually had radio waves and optical waves and X-rays detected from that event, that merger event, right? But those were all bursts. They were not like something that lasted. Supernovae last for months, and you can see it go peak and then come down, and then the width of the peak as well as the actual peak itself can be combined to create a standard candle. That kind of thing can't be done with these things. Okay, so I'll go to take 2-3 questions more because I have to go in 5 minutes. Yuvraj.
Am I audible, sir?
Yes.
So my question is on the Hubble constant. Like, we just found out that the universe is expanding, so which means like the expansion would have been slower in the past. So if I take a standard distance of 2 megaparsec from Earth, and the Hubble constant in the past would have been slower than what it is right now, because the Hubble now the expansion is also dependent on what is the age of the universe currently. So is it a misnomer to call Hubble a constant?
Yeah, absolutely. I mean, I told you before, it's not a constant. We called it the Hubble constant because up to what one could find, the slope seemed to be constant. It's now called the Hubble parameter. In fact, if you look in most cosmology books, ever since we found the variation in that, we've actually measured the variation, as you can see here, in that particular parameter. It's called the Hubble parameter. It's called H, and then people write it as H of Z, Z being the redshift. So H as a function of Z. It's no longer, and we call the Hubble constant H naught. You will see H subscript 0, and that means the value now. So it shouldn't be a constant. It's a total misnomer. Absolutely right. Okay, Neil, question next. I'm unmuting you. Yes. Go ahead.
So you talked about the C-feed variables. So in what life cycle of the star do they act as a C-feed variable? And can we predict that what star in a galaxy would become a C-feed variable next?
Yes. So I didn't go into that at all. In fact, I don't, and I suppose Dipankar Bhattacharya has not yet. Maybe he will this afternoon. if he talks about what happens. Where is he now? Has he gone off the main sequence in stellar evolution, or he's talking about compact objects? Are you attending Dipankar Bhattacharya's classes?
Yes, sir. So he is discussing neutron degeneracy pressure.
Yeah, so that's right. So he's talking about compact objects left behind. So I don't know whether somebody is going to do, this is a whole subject on its own, on what happens post main sequence to a star and what kind of instability is set in and stuff like that. So on the whole, it depends on the mass and constitution of a star, and so it is more or less possible to predict where it will go off the main sequence in that direction, going through the red supergiant phase into a red giant phase, or in the instability zone where you can become a Lyrae star or a Cepheid variable star. There are various kinds of such variables. Now that's an entire course on its own, so I'll not go into it, but if you are curious, pick up any standard textbook on stellar evolution, or even basic book on astronomy, astrophysics textbook, that is, physicist textbook, and you will find post-main sequence evolution, a chapter on post-main sequence evolution. Okay. I can recommend, for example, Frank Shu's Physical Astronomy. That's a very good book that discusses this in great detail.
So I had just one more question.
Okay.
That when we talked about the type 1a supernovae, you said that the peak brightness would give us an indication of the distance it is from us, but I couldn't quite get it intuitive. So could you just explain it once more?
Yeah, again, I didn't explain it very well, and again, I think you'll have to go and look up some things in the literature. I didn't explain it very well because it's rather complicated. Once they found that actually the peak is not the only parameter. Yeah, the light curve varies according to the origin of the supernova and its chemical composition. So from the spectrum, you can actually find certain parameters that later on we figured out that to establish the standard candle, you not only have to locate the peak, but you also have to locate to measure the shape, which gives you the width of that at half luminosity, the width of that. It's not quite a Gaussian. It goes up rapidly and then tapers off, and that width. So that width and the peak together can be formulated into something that is constant for each of these type 1a supernovae. And so that is why I did not go into that, but there is quite a lot of stuff in the textbooks that will explain that to you. So the standard candle depends on the peak, but it also depends on the shape. That's what I've Okay, I'll go and look at some questions in the quickly, because I really have to leave quickly in the chat box, and I find a good question from Abhijit Augustine, where you're saying that why are some galaxies moving towards us and most of them are moving away from us? And that's a good question. I think I talked about it at some point. And I said that, you remember, as the universe expands, the galaxies are expanding with the universe. But locally, galaxies can attract each other through their gravitational force. And if that attraction is greater than the push due to the expansion of the universe, then you can measure, then they're falling towards each other. So when Hubble measured these galaxies, he measured things like M31, which you know is falling towards us. One of those points was M31, Andromeda Galaxy. Another was M33, which is also near M31, which is also, we are attracting it. So those have blue shifts because they're falling towards us. And for all galaxies, you'll find that you'll have nearby galaxies that for which the gravitational force is so strong that it can overcome the expansion of the universe. So that's one question. Mehul Chakravarti is a question, which is, how do we so accurately know the composition of dark energy, dark matter, and ordinary matter in the universe? It's a very, very interesting and important question. I did not go into this at all because it's hard to do it in one lecture. But here is something that I haven't told you yet. And that is that dark matter, the reason we know that dark matter is not baryonic matter made up of quarks comes from something else. It comes from our knowledge of particle physics and the Big Bang, and our knowledge of the Big Bang is modeled from a cosmic microwave background, and this is exactly what the cosmology lectures will tell you. And from our modeling of the Big Bang, we know exactly the number of baryons, which are quark particles, protons and neutrons, that were produced as a result of the Big Bang. Because if that number, on that number depends something that you can measure, and that is, if you can measure the amount. So first energy was produced, and from the energy as the universe expanded, the energy cooled, and out of that protons and neutrons were produced, and the first bunch of matter that was produced was mostly hydrogen, but a little bit of helium. And the ratio of hydrogen and helium, which you can measure in very old stars, which were the first generation of stars, tells you what the original ratio of hydrogen and helium that is produced out of the Big Bang was. And that is crucially dependent on the total number of particles that were produced. And from that you can measure the number of baryons. And that tells us that from that we can account for only 5% of the matter in the universe. So we know that ordinary matter, how much ordinary matter there is. And then we can measure the amount of matter in the universe through various things that I did not talk about. I did not give you my dark matter lecture. There are many ways you can measure how gravitating matter in the universe through gravitational lensing, through measurements of masses of clusters, galaxies, and things like that. And we can see that there's a very big difference between the amount of matter that is predicted by the Big Bang and the amount of matter that you can measure. And so all this dark matter that is not baryons, is non-baryonic. They could be exotic particles. We don't know what they are. We don't know. Actually, you're saying, how do we accurately know what they are? In fact, we only know the protons and neutrons. We don't know what dark matter is made of. But we know that it is not made up of quarks. Okay? And dark energy, it's a total mystery. We don't even know what it is. You open a normal astroparticle physics journal now, and there are thousands of different speculations. So actually, we don't know what the universe is made of. We only know what our kind of matter is made of, and it's in the periodic table. Okay, so I think that is very interesting questions, but I really have to go because I have to go take my vaccine right now. So I am signing off. Thank you, and send me your questions through the Google Forms that have been set up, and I'll see what we can do about answering them. And I come back in the third week to talk about clusters, groups and clusters of galaxies. Okay, bye for now.